We've all been in a situation where the hands on the clock seem to be racing by, yet we still have plenty to finish before calling it a night. Sometimes it's tempting to grab a caffeinated beverage to keep you going. If you had to stay up all night working, which of these drinks do you think would keep you awake with more caffeine? Choose either the energy drink or the coffee drink, and then let's use high-performance liquid chromatography, or HPLC for short, to really find out. Nothing quite like the jolt of an energy drink to get you through a late night of work. Click the next arrow to begin. I'm Annie, and I'll be your coach during the next 10 or 15 minutes as we explore HPLC, high-performance liquid chromatography. It's one of the most powerful tools in analytical chemistry. HPLC is a separation technique that enables you to identify and quantify different components present in any sample that can be dissolved in a liquid. It can detect trace concentrations as low as parts per trillion. There are many types of chromatography, but for our experiment, we will be using reversed phase HPLC. Where is the HPLC technique useful? It permits product and component testing in many fields: medicine, food, vitamins, cosmetics, forensic science, and industrial chemicals. Special equipment is used for the HPLC procedure, and the focus of this experiment is to understand what happens inside the instrument during the process. In HPLC, a physical separation of components in the sample is achieved by forcing sample carrying liquid, called the mobile phase, through a chromatography column, which holds a packed bed of porous beads, called the stationary phase. Let's break that down a bit. HPLC begins with the injection of the sample, a mixture of components, into the flow of the mobile phase. When the sample reaches the column, the chemical characteristics of the porous beads allow them to interact differently with each component in the mixture. The difference in interaction causes components to stick with one phase more than the other. The components that prefer to partition with the stationary phase will take longer to flow through the column, and those that stick with the mobile phase will flow through faster. The differing retention times, in other words, how long it takes a particular component to flow out of the other end of the column, is what we see as separation. I bet you've already observed a chromatographic separation and didn't even know it. Like when black ink on a napkin gets wet. Have you ever seen how the black ink separates out into different colors when water wicks through the ink on the napkin? Select the drink you like to test first. Let's use liquid chromatography to see if the energy drink really does have more caffeine than the coffee drink. The first step is critical: preparing the sample. This can involve diluting or filtering the sample or other methods. In our caffeine experiment, we'll use black coffee with no condiments like cream or sweetener, and dilute and filter both drinks. Please drag the prepared sample to the correct location on the diagram. Thanks. A reservoir holds a solvent which acts as the mobile phase. Please place a solvent in the correct place on the diagram. Great! Keep in mind that a solvent is chosen based on the component you are testing for and the type of porous beads. This solvent moves the sample through the column, which is why this is considered the mobile phase. Now drag over the high pressure pump, please. Try again. That's correct. The high pressure pump is used to generate and meter a specified flow rate in the mobile phase. Then, the sample is introduced by injection. Drag the injector over next. Right. The injector introduces the sample into the continuously flowing mobile phase stream that carries the sample into the HPLC column. Choose the column now and put it in place. The column contains the chromatographic packing material, a porous bed of beads that is used to create a separation. This is called the stationary phase because the packing material is held in place by the column hardware and does not move, unlike the liquid mobile phase, which does. Let me show you a little more about what happens in the column. Click the magnifying icon and I'll tell you more. Carried by the mobile phase, the sample enters the column from the left, passes through the packing material, and exits at the right as shown by the green arrow. Our example starts with a column at time 0, or the moment of injection, when the sample enters the column and begins to form a band. The sample is really a mixture of 3 components, yellow, red, and blue dyes, but it enters the column as a single black band. Because different components of a sample have different binding affinities for the stationary phase, their movement through the stationary phase will be retarded by varying degrees, which affects separation, and in this picture, the yellow component is moving through fastest while the blue component is moving slowest. When you are ready, click the Continue button and select the detector next, please. Excellent. The detector is needed to see the separated components which form bands as they leave the HPLC column. Most compounds have no color, so we cannot see them with our eyes. In our example, a common UV detector monitors the UV absorbance of the mobile phase as it flows by the detector window. A band representing molecules of one component is detected by a change in the UV absorbance of the mobile phase going by. This detector type only works when the component or components of interest can absorb UV light. If not, then a different detector needs to be used. Click the magnifying icon and I'll show you a little more about this. Now let's look at what's happening inside a chromatographic column to make this separation occur and allow us to see it. We'll zoom in to look at the inside of the column at the molecular level. As you saw earlier, black ink consists of 3 dye components, red, yellow, and blue. When the mobile phase carries the sample through the stationary phase, the blue dye molecules are more attracted and stick to the stationary phase and tend to stay in place longer than the red and yellow dye molecules. In comparison, the yellow dye molecules are much less attracted to the stationary phase and move very quickly through the column. The red dye molecules are somewhat attracted to the stationary phase, but less so than the blue dye molecules. Over time, the different dye molecules separate from each other inside the column. In reality, including in our caffeine experiment, a sample can be anything that can be dissolved in a solvent. Usually compounds are colorless and the column wall is opaque, actually constructed of stainless steel to withstand the high pressures generated by forcing the mobile phase through the column. So we need a detector to see the separated compounds. After detection, the flow of mobile phase is waste. When you are ready, click the Continue button and drag the waste container over to the diagram to wrap this up, okay? Very good. The mobile phase exits the detector and is sent to waste, or it can be collected if needed. Before we move on, let me show you the output of the HPLC separation process, a chromatogram. Click the magnifying icon and I'll tell you more. As the mobile phase passes through the detector, its UV absorbance is converted into an electric signal that is sent to the computer collecting detector data. The computer plots this data on a graph called the chromatogram. By comparing the retention time of each peak with retention time of a standard from the same chromatographic system, you can identify what each peak in a chromatogram represents. Roll over each part of this chromatogram to learn more. When you are finished, click the Continue button. Now that you're familiar with how to read a chromatogram, let's look at the black ink example again. As each of the 3 dye components in black ink separate from one another and passes through the detector, a peak appears on the chromatogram. The size of the peak is proportional to the total amount of the component molecules. The total amount of the component in the sample is represented by the total area under the chromatographic peak. When you are ready, click the Continue button. We're now done testing the first sample. We'll look at the chromatogram results later. Click the next arrow to move on. Now select Let's use liquid chromatography to see if the coffee drink really does have more caffeine than the energy drink. I'm going to stand aside and let you build the HPLC system diagram. You remembered that prepping the sample up front. Next, we introduce... Nice work! At this point, it's time to inject. The all-important column is... Yes, the detect... Excellent! You correctly placed the components of the HPLC system in order and tested your second sample for our caffeine experiment. Now let's move into the results phase and analyze both chromatograms. Remember, a chromatogram is a representation of the separation that has been achieved using the HPLC system. Click the next arrow and we'll look at the results. Here are the results. Take a moment to look at each chromatogram. What do you notice about the differences in the three chromatograms? Now, before we analyze the results, I want to give you a chance to look at the chromatograms in detail. Starting with the standard, click on each chromatogram to see it up close. There are a number of peaks on each drink chromatogram, and one of these represents caffeine. How do we know which peak is caffeine? To really know, a caffeine standard, that is, a sample consisting of caffeine and no other components, needs to be analyzed on the same chromatography system. My colleague Bill is an expert with HPLC analysis, and he ran a caffeine standard on the system earlier today. The chromatogram for the standard looks like this. There is only one peak as expected, with a retention time of 4.3 minutes. So, when tested on this particular HPLC system, using the mobile phase or stationary phase combination, column length, and flow rate selected, the caffeine component in any sample will have a retention time of 4.3 minutes. Now click the Enter. Alright, you know that caffeine has a retention time of 4.3 minutes on this system. Let's look at the chromatogram for the energy drink sample. Can you identify the caffeine peak in this chromatogram? Click on the peak you think represents caffeine. Yes, that's the one. Now click the coffee drink chromatogram Now how about the caffeine peak for the black coffee sample? That's it. Fantastic. I think you're getting the hang of this. Click the next arrow to move on. Okay, now that we've figured out which peak represents caffeine in the two chromatograms, we can finally get to the question that brought us here. Which drink has more caffeine? We can compare caffeine peaks in the two chromatograms to get this answer. In the note above, we've summarized the few things to simplify our work. When you're ready, click the next arrow to... As you already know, peak height and peak area, also known as the area under the curve, are proportional to how much of a component is in the sample. This means that the injected samples represent the same proportion of the whole drinks, thereby allowing a straight comparison of the chromatograms to determine which drink has more caffeine. Simply speaking, the sample with more caffeine will have a greater peak height and area. Do you have your final answer in mind? When you're ready, click the next arrow to make your... So which sample? That's right. This 12-ounce black coffee has more caffeine than the 12-ounce energy drink. Click the next arrow to move on. Congratulations! You proved you understand what goes on during the HPLC process. I've worked up a thirst and I'm ready for a drink. Can I offer you a nice cold bottle of water? By the way, a lot of times when you're using HPLC, you'll want to know the specific amount of the components of interest in the sample. To get this information, create a standard curve. And sample preparation is usually much more complex than in our experiment. In these cases, you have to perform some calculations to draw correct conclusions about the original sample from the HPLC results. Because creating standard curves and extrapolation calculations are important analytical skills, and we've only touched on them briefly today, I recommend you download and/or print out a takeaway activity to learn more. Don't forget to print out your certificate before you go. Good job!